We are now continuing on. We've just finished section 10.2. We're going to look in this video at 10.3, and we're going to look at a special case of these more complex equations. So what we're going to do is put these two to 0. That means essentially there's no damping. So we get dv dz equals minus L di dt, and di dz is equal to minus c dv dt. Now we have a little bit of work to do. We're going to differentiate this with respect to z. So we're going to do that, differentiate that with respect to z, and this with respect to t. So let's do that. And this one with respect to z. No, not with respect to z, sorry, with respect to t. So that's what we want to do. So we get a second derivative of v with respect to t. Now look at this term here. It's a mixed derivative of I with respect to t and z, and the same here. So these terms, the right side of this differentiation and the left side of this are the same. So I can take this and substitute it in here. So this term goes in there. And what do we get? Well, the minus L and the minus C combine to positive LC times that. So finally, we get this. We recognize that from the homework exercise 3. It's just that v was equal to u. So the speed, if we have a wave, the speed v is equal to, or v squared is equal to 1 over LC here, or LC is 1 over v squared, and therefore v equals 1 over the square root of LC, if we just take the positive root. Now, right away, we know the solution for the voltage, V, because we've seen this before. And so we get that V of, in this case, Z and T, of course, is equal to F1 of T minus Z over V plus F2 of T minus Z over V. And that should be plus F2. So this one, minus sign, represents, as we know, waves traveling to the right, or forward waves. And this is waves traveling to the left, or backwards waves. So we go V plus V minus. And this is in Haight and Buck, and it's equation 14. So we have the voltage. Now, what I'm going to do is I'm going to erase all this because I don't have any space anymore, and my head's just kind of sitting between a spaghetti of equations. And then I'm going to write the currents down, and we'll get some interpretations as to what's going on. So bear with me, and I'll write after I erase this part of the board. Now, what we can reflect on while I'm erasing is the fact that we did some very hard work to set up that we could write the solutions of this equation for the voltage. right away. And we know what that actually means. And there's nothing to derive here because of the previous work that we've done. We can actually apply this work. So want to find the current now from the voltage. And we can do that fairly straightforwardly because of this equation here. For the current. In order to do that, we use this equation. dV dz is minus L di dt. And I know we have V plus and V minus as before. So what is V? Just to remind ourselves, V equals Vf1 of t minus z over V plus F2 t plus z over V. So that's the equation that we have. Now, differentiating that with respect to z gives us di dt. So let's make a note of that. di dt equals minus 1 over L dV dz. So we'll differentiate V with respect to Z, multiply by minus 1 over L. That will give us di dt. di dt equals minus 1 over L. Now, this with respect to Z, we differentiate with respect to the argument, which will indicate just by a prime sign. So this means differentiate with respect to t, but we use the chain rule. It's df, the argument dt, but the derivative of t minus z over v with respect to t is 1. So that's fairly easy. And now we have also the derivative of, in terms of z here, we have 1 over v, right? So dv dz is df, the argument dz. So that's from the first term, and there should be a minus sign here. And for the second term, it's going to be plus 1 over v f prime of t plus z over v. So there's the time derivative of the current. Now, here's the tough part. We have to integrate this with respect to time. The argument is not with respect to time, but a time shift, t minus z over v. Time shift, t plus z over v. But when we integrate, it doesn't matter whether we integrate with t or t plus a shift, because that can always be appearing in the limits of integration. So to get I out of this, we just integrate with respect to t. So the arguments actually drop out. And so I is equal to, you got to be careful with the signs here because there's a minus 1 over L in front. So this first term, minus 1 over L minus 1 over V, that's just 1 over LV. We integrate, we get F1, forgot the 1s and 2s, F1 of t minus z over v, minus, because there's minus 1 over L times 1 over v, Now, this is where the complications come in all this analysis. This is V plus V minus. Forward traveling voltage wave, backward traveling voltage wave, forward traveling current wave, plus backward traveling current wave. But notice the difference. First of all, there's a scale factor, and there's a minus sign. So compared with this F2 has a plus sign in front, this has a minus. So there's a polarity reversal here. So in order to get a picture of what's going on, it's going to be a little bit tricky to relate I plus and I minus and V plus and V minus in a diagram. Forward voltage, reflected or backward voltage, forward current, backward current. And the question is, what are the units of this term here? Well, if you look at this, this is apart from the minus sign. That has to have units of volts, and this has to have units of amps. So this has units of impedance, and it's called the characteristic impedance of the line. Now, I want to show a picture of what this looks like for interpretation. So we'll see that in 10.4, and I'll just erase a part of this so we can fit the picture in. Don't have to spend time erasing the whole board. So let's see what it looks like, and if I have to erase a little more. Oh, that's good. So a bit of rough and ready here, but enough to explain the picture. Now, we have some transparency here, so I'm going to use my finger. So the voltage comes in here, V plus, and then it's reflected as V minus, just like the arrows show here. And the voltage is the voltage difference across the top of the line and the return. Let's look at I plus. I plus is a current that goes all the way to the end, and the return for I plus is backwards, so as shown here. I minus is polarity reversed, so that means its reflection starts here, and the return for I minus is given by this one here. So I plus, sorry, it should be the blue. Here's I minus going forward and coming back. This diagram is a little bit confusing. So I plus, forward and back, and I minus, which we normally think of this way, is going in the opposite clock sense. So it's going this way and coming back. And that diagram 10.4 in the text is very confusing, so I hope you understand what's going on. The reason the blue arrows are the way they are for the current is due to the polarity reversal. And that's it for section 10.3.